Hi everyone, we are Group 5 and today we presenting our project on the principal sets of subject advanced strength of material. So hi, I'm Darshan RAMASAMY from Faculty Mechanical and this is our teammates Mr. Muhammad SIRAJUDDEN SHAH, SHAKIR and FARIS. Okay, this is the overview. This is the structure of our presentation. We will start the introduction followed by our objective, then cover the theory, the formula. We will also solve the example problem and end with the conclusion and reference. So this is our introduction. So when the external load are applied to the structure of our material, internal stress development. So this internal force determine how the material react to the loading. This stress vary in the direction of magnitude depending on the plane of observed. Because of the non-uniform distribution, we are the focus on the most significant, the principal stress, which is the higher lowest normal strength in a material. Okay, the for the introduction after two things, it is mean the project goals and what is the principle of stress. Okay, let's see about project goals. So our main objective to is understand to analyze the principal stress, the maximum and minimum normal stress acting on the passive plane within the material. So we will explore the organic and important application in the engineer, especially in the material design of analysis. So then second thing is what is the principal stress? So let's go. The principal stress occur on the particular plane where the stress is zero. So these planes are critical in the design because they tell us extreme value of the normal strength and material experience. So that's all. Okay, for this section we talk about theory. So theory have two things. The first one is stress state of structure can result from, and second thing is stress component. Okay, let's see about the stress state. Okay, first one is normal stress. Stress is perpendicular to the plane, and the second thing is shear stress is the parallel to the plane, and the second thing is stress of component. Have four things in the components. The first one is axial loading, the produce of normal strength, and second thing is torsion, cause the shear stress, and the third thing is bending, include the compressive and tension normal stress, and the fourth thing is a combining loading. A combining loading of the above. Okay, for follow this part have key components. So they have the four components over here. So let's start about first one. The first one is a principal stress. So this one, the maximum and minimum normal stress at a point occur of the plane where the shear stress is zero. And the second thing is the maximum shear stress. So this one is the greatest value of the shear stress, a point of which occur at the 45 angle and from the principal plane. So the third thing is combination stress analysis. So this one is superposition is used to combine stress from the axial bending and shear and torsional and loads. And the fourth one is mole circle. So mole circle is a graphical tools, a visual stress state to determine principal stress and find the angles of the principal plane. Okay, for let's see about the next part. So next part we're using of the list of formulas. So let's see about it. So the first formula we're using in general stress transformation equation is normal stress and shear stress. So second thing we use formula is principal stress. So for here we use three principles. So the first one is principal normal stress and maximum shear stress and the angle of principal of plane. Okay, for the third formula we are using is beam stress. So normally you use is normal stress due to bending, where My is bending moment, the y distance of the neutral axis and high for movement of inertia. So the shear in the beam where we use the V is the share of force and Q is first moment of the area and B is within of the beam. So we see about the fourth formula we're using in torsion in the shaft. The torsion shear strength, and where is T for torque and R for shaft radius and J for polar moment of inertia. And the follow part is angle of twist. So L for shaft length and G for shear modulus. Okay, the following formula we are using in this part is fifth is combined loading. So combined loading have two stress, so normal stress and shear stress. So these two combine stress to find the principal stress and maximum shear stress. And sixth thing we use is application. So beam design ensure that maximum stress doesn't not exceed the material allowable. They have two designs, so we are explaining it. So shaft design to calculate the shaft diameter and based on the torsion shear stress. And the second thing is combined loading, the superimposed stress to find the resultant state.
Question 1. An overhanging W920 times 449 roll steel beam supports a load P as shown. Knowing that P equal to 700 kN, A equal to 2.5 meter, and allowable stress equal to 100 megapascal. Determine A. The maximum value of normal stress in the beam. B. The maximum value of the principal stress maximum at the junction of the flange and the web. C. Whether the specified shape is acceptable as far as these two stresses are concerned. So this is the solution for the question 1. So we have given the data load P equal to 700 kilonewton and the distance from support to load A equal to 2.5 meter, and the allowable stress is 100 megapascal, and the beam section that we have given is W920 times 449. So for the A, we use the bending stress calculation. First, we need to find the maximum moment equals to so RA times A equals to 700 times 2.5 equals to 1750 kilonewton meter. Then we use the bending stress formula. Maximum stress equals to maximum moment over section modulus equals to 94.59 megapascal. Then for the B, we use shear stress calculation. For first, we need to find the neutral axis y. Then second, we use determine distance to centroid of flange y. Then we use the average y for the q, and we find the area of flange. Then we find the first moment of area qb. Then using the shear stress torsion xy formula, we find the combine bending and shear stress. Then we do the bending stress at flange web. Then we combine maximum, combine normal stress and principal stress. So we get the answer 93.93 megapascal. Then see the conclusion. We find the maximum bending stress equals to 94.49 megapascal, and maximum principal stress is 93.93 megapascal, and the allowable stress is 100 megapascal. So since all the calculated stress are less than the allowable limit, the W920 times 449 section is acceptable for the given loading condition. Thank you.
Assalamualaikum and good day. My name is Muhammad SHAKIR, MA22149. I will continue with sample question number 2. So in this question, we are given a brass post shown and a couple of 1.4 kN is exerted on the brass post with a 10 kilonewton force. So the diameter of the brass post is 65 millimeter, and we have to find the principal stresses and maximum shearing stress at point H and point K. Okay, now for the solution. First, we need to identify out the geometries and perform a load analysis. Okay, so after we do that, we get V equal to 10 kN. So to calculate the M, we just multiply the 10 to the power negative 3 to the distance, which is 240 mm, and T is given, which is 1.4 to the power negative power 3. and C is just half of D, which is D is given, and then J is pi over 2 C to the power 4, and I is half of J. So because this is a semicircle, the Q value is equal to 2 over 3 C to the cube. Okay, now after we done all that, we can move to the to find the stresses at point H. So because point H lies on neutral axis, the sigma is equal to 0. So we only have stresses due to torque and stresses due to shear. So to find the stress due to torque, we use the formula tau equal to Tc over J, which we will get 25.963 MPa, and due to shear, tau is equal to Vq over It, which we will get 4.018 MPa. So the total stresses is just the combination of tau torque and tau shear, which we will get tau total is equal to 30 MPa. So to find the principal stresses, we use the Mohr circle. Okay, so the formula for the Mohr circle is, tau sigma is equal to sigma c plus minus r. So we know that sigma c is equal to 0 and r is equal to 30. Is equivalent to the value of tau total. So for the calculation, we get sigma max, which is equal to 30 MPa, sigma min is equal to negative 30 MPa, and tau max is equal to R, which is also 30 MPa. Okay, now for the B part, stresses at point K. So the stresses at point K now, stress due to shear is equal to 0. So we only have due to torque and due to bending. So for the stresses due to torque, the formula is still the same, which is tau equal to Tc over J, which is the value is 25.963 MPa. And for stress due to bending, we use formula sigma equal to negative mc over J, which we will get negative 89.016 MPa. So to calculate the principal stresses, we use a Mohr circle. So for QC, we just have to uh, divide the sigma bending by 2, which will get negative 44.508 MPa, and the R is given by the formula. We use uh, QC sigma C plus with tau square, which we will get R is equal to 51.527 MPa. So using the same previous formula, the sigma max is equal to sigma C plus R, which we will get 7.02 MPa, and for the sigma min is sigma C minus R, which is negative 44.508 minus 51.527, which we will get negative 96 MPa, and tau max is equal to R, which we already calculated, which is equal to 51.5 MPa.
Assalamualaikum and good morning. My name is Muhammad Faris bin NORIDZUAN and my number metric is MA23013. And so the sample question 3, the first is a thin strap is wrapped around a solid rod of radius, which is C is 20 millimeter, as shown in the diagram, and knowing that the length is 100 millimeter and force is 5 kilonewton. So determine the normal and shearing stresses at A. The first question is point H and at B is point K. So the first one is we need to identify all the forces. So we know that the question is the strap pushed downward on the front side of the road and wraps halfway around the road. So they produce three types of loading effects, which is the force at the cross section, containing points H and K. So the first one is bending moment. Because the force is applied at a distant length, it causes bending about the horizontal axis of the road. And we know to calculate the bending moment is force multiplied by length. So this will create normal stress at points H and K. So for the point H on the outer side, which is a max tension, as for point K on the neutral axis, no normal stress for bending. So the second one is torque, which is torsion. We know that the strap also wraps around the rod, causing it to twist. So to calculate the torque, which is force multiplied by C. So this will create a shear stress due to a torsion maximum at the outer surface H and K. And the last one is shear force, which is V. The vertical force F is equal to 5 kN, will also causes transverse shear in the cross section. This contribute additional shear stress, especially important at point K near the centroid. So for the step 2, we need to calculate the bending moments. The equation for bending moment is force multiplied by length. So we have the force which is 5 kilonewton and length is 100 millimeter. So we get 500 newton meter. And the second one, we need to calculate the torque. So the torque is, the equation for the torque is F multiplied by C, which is the center, and the force is 5 kilonewton, and the center of radius is 20 millimeter. So if we sum up, we get 100 newton meter for torque. So this tells us the strap cause both bending and twisting in the rod. So the third step is we define our section properties using the radius, which is C, 20 millimeter. So we need to calculate the moment of inertia. The formula for moment inertia for cylinder is pi over 4 multiplied by radius, which is power of 4. So if we substitute the value, and we get 1.2566 power of 97 meter power of 4 for moment inertia. So for the polar moment of inertia J, the formula is pi over 2 multiplied by C power of 4. So if we substitute the value, and we get 2.5133 times power of negative 7 meter power of 4. So the next step is we need at point H, which is on the outer surface, we need to calculate the bending stress. For the formula is MC divided by I. So if we already calculate M. So if we substitute the value, we got 79.58 megapascal. So that's a normal stress for bending. So next we need to calculate shear stress from torsion. So the formula for shear stress torsion is TC divided by J. We already calculate T, C and J, and if we substitute the value, we got 7.96 megapascal. So the next step is we use the Mohs circle. So first we need to find the center of the circle, which is stress S divided by 2. We got the 39.79 megapascal. So the radius is calculated by square root sigma stress x over 2 power of 2 and plus by shear stress xy power of 2, and we got the value 40.57 megapascal. So the next is we need to calculate the principal stress, max and min. So the max, we know that the calculation, the equation for to calculate the stress max is stress C which we calculate and plus earlier and plus by R. With we substitute the value, we got 80.35 megapascal. And for sigma min, and for stress min, the formula is stress C minus R. If we substitute, we got 0.74 megapascal. So the maximum shear stress is equal to R, and which is 40.57 megapascal. And shear from torsion, we know that we got 7.96 megapascal from earlier. So the next one, we can calculate the shear from vertical force. And the formula is PQ over IT. And if we substitute this value, and for the Q, we know that it is a semicircle, and the formula for semicircle is 2 over 3 multiplied by radius power of 3. So if we substitute, we got 5.333 times power of minus 6 meter power of 4. So if we substitute the value for the thickness, which is 2 multiplied by C, and we got the thickness around 40 millimeter. So if we substitute the value, we got 5.31 megapascal. So we can combine the shear stress. So if we combine the formula from above, which is stress for torsion and plus by shear from vertical force, and we got 13.27 megapascal. So for the most circle for point K, we know that normal stress is 0. So the max principal stress we can calculate from the formula earlier, which center is stress X. Stress X, we got 0. So the center is 0. And R we can calculate by square root. Stress X 0 plus stress Y 0. So plus by shear stress power of 2. So we got 13.27 megapascal for sigma max. For sigma min, we got negative 13.27 megapascal, and we know that sigma max shear max is equal to R, so the value is 13.27 megapascal. So to summarize, we know that point H has high normal stress and moderate shear, which is dominated by bending. So point K has no normal stress but feels combined shear from torsion and vertical load. So that is for me. Thank you.
As for the conclusion, a material's maximum and minimal normal stresses under a specific loading were covered in the presentation. These are known as primary stresses. By shedding light on material behavior, it demonstrated their importance in engineering design and analysis. Additionally, the talk covered a number of primary stresses applications, including combined loading, beam design, and shaft design. Lastly, the lecturer used the formulas and examples to clarify the ideas and offer useful advice. Thank you.